There you go. Okay, the first thing is, if I had been here last week, it's possible that a couple of you, you had something unfinished or unresolved about your first quarter grades. If I had been here, would you have talked to me last week? If you had, I want you to talk to me this week. Even though the reports card is going to come out, I can change it. So I need you to say, if I would have been here last week and you said, I need to talk to him about this, I think you need to talk to me. I'd like you to talk to me this week. I'll be here Wednesday. I have meetings, but I'll be here after school today and tomorrow and Thursday. I'll be here at lunch all 3 days. You can actually come in early now, you know that? And get scanned, at 7:30, 7:45? And so if you want to come in the morning, it wouldn't even take very long. And I just want to make sure that you and I can close the book on the first quarter. If you think, no, that's my grade, I didn't have any zeros, that's my grade, then I probably won't see you. But if you think there's something wrong with the grade, I really want to see you, honestly. And because I want you and I to be on the same page and said, we both agree that that's the grade that you should have got for the first quarter. Okay, is everybody there? Okay, that's important to me. All right, now, next. What you did in class was on day 1 and 2, you mainly took notes on chapter 3 and you had to draw some diagrams. Is that correct? Okay. If I ask you to write down, don't do it. If I ask you to write down 7 things you remember from that, could you remember 7 things from your notes? 7 words, 7 ideas, some diagrams. Okay. So if not, then you must have just been going through the motions. You got that? And now, the next thing you did was you got in small groups and you answered the questions, didn't you? Is that correct? Do you remember those? Now, if you answered questions, you had to know something about the chapter to answer the questions, right? So really, you're done with chapter 3. Now, I had actually taught one day before I left on chapter 3, and I'll remind you of that today. I'll review that today. But then I also want to do some more stuff with chapter 3, and it is the shortest chapter in the book. I'd say it has the least difficulty. It's the least difficult chapter in the book. Sorry. Okay. So anyway, so what we do, my plan is, and I had mentioned this before, I said we're going to do factor label with chapter 3 and then have a test on both of them. And that's going to be Thursday. So here's what's happening on Thursday. On Thursday, the first part of the test will be factor label. And I'll give you probably 3, I don't think I'll do 4, I may only do 3 factor label questions. It will not be type 1, so it might be type 2, 3, or 4. And you've been certified with that. Do I still have any of your factor label stuff, or do you have it all? I'll look again, but I think you already have the certification, you had your quiz, is that right? Okay, so that's the first part of the test. And the second part of the test is chapter 3. And that's what I want to spend today and Wednesday on. You already spent a lot of time on chapter 3. I'm just going to fill in the gaps today and Wednesday. This could be a really good test for some of you. I don't consider this to be the factor label. If you don't get every one of those right, that's your fault. Now, we can practice. If you want to practice some, I can do that with you. But you're certified, aren't you? You should be able to do any factor label problem on there, and I think you will be able to. My goal is to do chapter 3 today and Wednesday, and then you'll have a test on Thursday, and it'll be on chapter 3 and factor label, like that. Okay, and then I'm kind of excited because I like the chapter a lot next week. Next week we start the chapter on atoms, ions, isotopes, and stuff like that. I'm going to have to change my format a little bit this year. They want to have exams in December, and but yet you come back for almost 2 weeks in January, and that's still part of the second quarter. So what I'm going to do is I'm going to rearrange things so that we do more of the book stuff until exams, and when I get done with the book stuff where I want to be, then we'll do labs from that point on. So I'm going to postpone some of your labs until we get the book stuff done and have our exam. And then at that point, you may do labs for almost 2 weeks in a row. And I'm just going to do that because I don't have the lab stuff on the exam anyway. So, okay? And that's where I'm going to do that. And then we'll start the second semester like that. All right, well, here we go. If you don't have your book with you, that's fine. But I'm going to do a really quick review of the lesson I had before you left. And this is also on video if you ever want to go watch it again. I talked about states of matter or phases of matter, and we talked about who has a definite shape, but not only who has a definite shape, but why. Why they have a definite shape. Who has a definite volume? Why? Who's compressible? Who's not? Can you do this without memorizing the chart? Has this become part of you? You said, just ask me any day. Any day, ask me. Are solids compressible? Let me think about it. Let's see. Can I compress this into this size right here? No. All right, what about liquids? Can I take a gallon of milk and compress it into half a gallon of space? Let me think about that. No, I can't do that. There's no compressed liquids. What about gases? Can you compress them? Okay, so see, you keep thinking memorize. No, just it should be in you. What about definite shape? Who has a definite shape? Solids? Whoop. Hey. Definite volume. What do you think? Definite volume? Does it change volume? No. What about gases? Definite shape? If I take a balloon and twist it, then I have a new shape? What about, what if I take a balloon and I squeeze it? Is it compressible? And all those are for the same reason. Why do you not have a definite shape? We're so far apart, we don't keep ourselves locked in, we don't attract each other into that shape and keep it. We do. And you're compressible because there's a lot of emptiness. There's nothingness between the particles. If I had a balloon of helium and it was all helium, and I said the particles are kind of far apart, what's in between the helium? And you might say, air. No, it'd be nothing. Nothing? What do you mean, nothing? What if I take a solid and there's a teeny tiny space between these particles? What's in between there? Nothing. And if I had to draw a liquid, I would draw it almost pretty much like a solid because you can't compress it and it has a definite volume. Okay, is that enough review? Let's go down here. What do you call it when you go from a solid to a liquid? Melting. What if you go from a liquid to a solid? Freezing or solidification. What if you go from a liquid to a gas? Boiling. What's another word? Vaporizing. And if you happen to do it at a temperature below the boiling point, evaporation, right? What do you call it if you go the other way? What about from a gas back to a liquid? Condensation. Okay. What about a liquid into a solid? Freezing. But a lot of people don't like to say that liquid gold was frozen. They like to use frozen for water, but they usually use this word. If you were an engineer, you'd say the solidification of gold or something like that. And what's this special thing where you take a solid and it goes directly to a gas and it skips the liquid phase? Sublimation. Okay? All right, let's review there. Next. Oops. Let's try and find your paper. All right, here we go. I'm going to go as fast as I can, but since you've already know all these words, you've answered questions, we should be able to go at a pretty good pace today. All right, do humans like to classify things? Yes, they love it. They love to put people in groups. They love to put everything in groups, okay? Now, when chemists said, we're going to study matter, we're going to say, okay, how are you going to group them? Here's one way to group them. It has to do with how many ways can we make you? And that's called composition. Constant composition means there's only one way to make you. And if you are, you're called a pure substance. Now, what if there are many ways to make you, and we have a name called mixture? Hey, let's think of something. Let's make some water. You make water in Germany, and you make water in Japan, and you make water in Rhode Island. And when they make water, how's it going to be made? Whatever process they use, won't the water come out to be two H's combined with one O? Won't it be H2O? There's no way that you can make water different than H2O. It has constant composition. So the things that are pure substances that have constant composition are elements and compounds. Okay, so if I have a gold atom in Russia, a gold atom in Bolivia, a gold atom in Waco, Texas, then it's the same composition. It's a gold atom. All right, so what kind of things are pure substances? Elements and compounds. Now, because it was more than a week ago that I gave this talk, how do you know if something's an element? It's only made of one kind of atom. And how do you know what kind of things on the planet are only made of one kind of atom? That's right. It's the periodic table of the different kinds of atoms that we know of in the universe. And so I don't care what you think. If you think there's an atom of air, you're wrong because it's not up here. Well, I know there's an atom of plastic. You're wrong. How about skin? No. I know there's an atom of wood. No. I know there's an atom of water. No. If it's not up here, there's no such thing as an atom of it. Get that? So if you're on here, you have a chemical symbol, and you're a pure substance. And what about these other guys? CO2, H2O, C6H12O6. Those are called compounds. Compounds are where atoms are chemically bound to another chemical, to another atom, and you have more than one kind of atom in there most of the time, and they're held together with chemical bonds. How in the world are you supposed to know if something's a compound? Well, I'll give you a clue. It has to have a chemical formula. Okay, water, does it have a chemical formula? Yeah, H2O. Glucose, C6H12O6. Okay, then you're a compound. How about carbon dioxide? Yes, CO2. What about dirt? I think there might, no, there's no formula for dirt. Well, how about plastic? Now, unfortunately, there are different kinds of plastics, and the different kinds of plastics, each specific one might have a formula. Get that? So plastic is kind of unique because it is a compound. Now, if you think about that, if you're not an element or a compound, then where do you belong to? Mixture. Now, what are mixtures? That means you can make them many ways. Most of the things on this planet are mixtures. Hey, let's make some salad. You make a salad, you make a salad. Are they identical? They're not identical, are they? All right, everybody, your assignment tonight, go make some salt water. Bring it back and we'll analyze it. Is everybody's salt water going to be the same? Yours is 1% salt. Yours is 10% salt. Yours is 3.5% salt. How come you didn't make them the same? Because you can make it differently, can't you? How many ways can you make salt water? Many. How many ways can you make a salad? Many. All right, what about... Hello. Okay, thanks. All right, Ty, thanks. So I know that you're very good at memorizing. If you're an honor student right now at this school, you're probably good at memorizing, but you've got to be willing to do more than that, okay? Because I don't want you just to memorize this. It's got to make sense to you. Let's go over here. This book says that you can split mixtures into two kinds, homogeneous and heterogeneous. What's that mean? This has to do with not your composition, but what you look like. What you look like. If I look at you and it looks like one material, it looks like homogeneous. Homo means the same, doesn't it? Anyway, if it looks like one material, I know you're a mixture, but you look like one material. Now, what's a special name for a homogeneous? I always ask this on the test. What's a special name for is his dad a police officer? Oh, just kidding. What do you call a homogeneous mixture? You know there's many ways to make it, but when you look at it, it looks like one item. Starts with S. Solution. Okay, so a homogeneous solution, a homogeneous mixture is a solution. Can you remember that? Now, why is it homogeneous? Because when I look at it, it looks like one thing. Why is it a mixture? Because you can make it many ways. Hey, let's make some Kool-Aid. How many ways to make Kool-Aid? And a lot of you are thinking, one, if you follow directions. What if you don't follow directions? Well, I guess you could make it 100 ways. You're right. Isn't that right? Can I make Kool-Aid? How many people, you ever taste coffee and said, oh, you don't make coffee like I do? Well, there's many ways to make coffee. Coffee's a solution. The one I think you're going to have trouble with is, yes, I could put something like salt and water, and I could put them together and mix them, and it looked like one material, and I call it salt water. But I know I mixed them because I did it. Well, I put a little less salt, a little more salt. It's still salt water, isn't it? That's the easy one for you. Did you know if I go to the store and buy some rubbing alcohol, I can buy a rubbing alcohol bottle and it'll say 90% rubbing alcohol. 90%? Don't I get the whole bottle? Aren't you going to give me the whole bottle? Yeah, I'll give the whole bottle. What does it mean by 90% rubbing alcohol? That's right. If you had 100 milliliters of that, 90 milliliters would be made out of alcohol. And 10 milliliters would be what? Water. Sorry. Now, a lot of companies, because they know that, what are you going to use rubbing alcohol for anyway? Some people used to use it to rub on people's muscles. And it would get in there, and that's why it's called rubbing alcohol, because if you had leg cramps and things, they would do that. They would rub it with rubbing alcohol. It even had a little bit of slicky stuff, lubricant in it. And it would make it so you could do that. And it would actually massage the muscles, and it would take the cramps away. That's why they called it. You ever wonder why they call it rubbing alcohol? Well, that's what originally it was bought for. But nowadays, I bet your parents don't use that for that. I bet they have it in the bathroom somewhere. And if they want to sanitize the bathroom sink, do they do that? Do they put it on a paper towel or something and coat everything? Do you guys do that? You guys never cleaned the bathroom, right? Okay. I use Clorox? Okay, you could. Okay. But rubbing alcohol can be used to sanitize things. But a lot of companies say, hey, guess what? 70% rubbing alcohol. And they say, let's try it. And they try it, and guess what? They still sell just as many. What does that tell them? We're saving money by putting more water and less alcohol. And the customer says, it does what I expect it to do. So the company just pat that person on the back and said, thanks, you just saved our company a lot of money this year. If you go to the dollar store, you'll find rubbing alcohol. It says 50% alcohol. What do you think about that? Now, there's some people that think that's good enough. That's good enough. And they'll keep buying it, won't they? Whatever you're buying it for, if it works for what you think it works for, then, all right, we'll make some more money and you'll be happy and we'll be happy. So this is a solid dissolved in a liquid, but alcohol is a liquid dissolved in a liquid. Is that correct? Could you have a gas dissolved in a liquid? Could you dissolve a gas in a liquid? What do you think? Raise your hand if you know an example. Okay, I'll give you a clue. Fish do not breathe water. Okay? Fish breathe air dissolved in the water. They dissolve, there's oxygen that's actually dissolved in the water, and they breathe it. Now, you don't have to do this experiment, and please listen, if you ever even think about doing it, don't do it the wrong way. Let's say you have a goldfish, and you get some water, you get a gallon of water, and you boil it. And just boil it for 30 minutes. That'd be enough. And you boil it for 30 minutes, then you put it in a container, and you want to let it cool, but I want you to seal it off. I want you to seal it off so no air can get back in there. You've already boiled all the air out. And what I want you to do is don't let any air back in there. Now the key is making sure that the water is cool. Then you put the fish back in the water and the fish will drown. Because the fish is not breathing water, he's breathing the oxygen dissolved in the water. And if you take the oxygen out of there, he will drown. You had your hand up, I didn't call on you. You had another example?
I don't think it's right.
I think it is. You're going to say carbonated drinks?
Yeah.
All right. Carbonated drinks. They discovered this in the 1800s, and they found out if you had CO2 and just had some CO2 and ran it back and forth with some water, you could make sparkling water. And some people said, refreshing. And then they found out later you could put it with some other things like colas, and they made soft drinks. And soft drinks are carbonated. And they actually have dissolved carbon dioxide in the water, and that's what gives that little tingly taste when you taste it. And then I think the hardest one is solids dissolved in a solid. Can you think about that? How about a solid dissolved in a solid? Now, there's a little trick there because it's hard to dissolve a solid in a solid until you melt them first. So I kind of tricked you a little bit. But we do this all the time. They're called alloys. Now, alloys are mixtures. What kind of mixtures? Homogeneous. They're mixtures because you can make them many ways. How many ways can you make steel? Many, many ways. Now, iron is almost always the main ingredient in steel, but you can make nickel steel, chromium steel, carbon steel. There are many kinds of steel. Brass. Brass is copper and zinc. And how about the Bronze Age? You ever heard of the Bronze Age? We've been learning how to make different alloys for a long time. Now, have you ever heard of this? 24 karat gold. Ever heard of that? I can tell you, I can look up the story about the carat and why 24, but whatever it is, 24 karat gold is 100% gold. That's it. You can't get 20. Oh, I have 26 karat gold. No, you don't. That's it. 24 karat gold means every one of those atoms in there is gold. But I bet most of you do not have 24 karat gold in your house. But I bet some of you have a ring or maybe a necklace. Do you have anything made of gold in your house? And do you ever check to see what it says on there? I'd say most of you have 18 karat gold. What does that mean? I'll show you. If you have a calculator, do that right now. You have a calculator? Am I on the screen?
Yes.
I'm not on the screen. Okay, sorry. Boop. All right, little calculator. All right, 18 divided by 24. 75. I should have known that. Did you know that when you have 18 karat gold, only 75% of that gold is gold? I mean, all the gold's gold. But 18 karat gold is not pure gold. It's an alloy. Now, what else is in there? I don't know. Sometimes they use silver. If they use silver, 25% silver, 75% gold, it's called 18 karat gold. And some people call that white gold. But they could use copper. You could use copper and gold. And guess what happens when you mix copper and gold? It still looks like gold. So people say, that's gold. 18 karat. This stuff here is nice and expensive, but it's soft. You would never, ever want to make a ring out of 24 karat gold. You wouldn't want to make a necklace out of 24 karat gold. As soon as you turn the wrong way, snap, it will snap. You make little rings out of gold, they'll snap. If you make this kind of ring out of gold, as soon as you grab a hold of something, your ring turns into an oval. They want something that's harder, so they make an alloy. Okay? In this country, if you're not at least 12 karat gold, if you're not at least 12 karat, you can't even use the word gold in your advertisement. So humans, being as they are, they have these commercials. You can get fine imported Italian gold. You can get a gold chain for $25. Wow, that should cost $400. I get it for $25? I'll do it. No. First of all, in our country, if it's not at least 50% gold, you cannot sell it as gold. But not in other countries. So when you say imported Italian gold, I don't have to use the definition for the United States, do I? So what if it was 2% gold? Still look like gold. It's only 2%. Thanks. You just paid me a lot of money, and you thought you had a great deal, right? Anyway, they like to do that kind of stuff. Do you understand alloys? Okay, now, here's the hardest thing you're going to do today, all right? I'm going to have you do another chart, and this will tell me whether or not you are just a memorizer or whether or not you understand these words. All right, instead of the first question being, do you have constant composition or variable composition, I want you to make a chart for me, the classification of matter, because the first question I want to ask is, when I look at you, do you look homogeneous or do you look heterogeneous? All right, go ahead, finish the chart. Use all the words that we use on this chart, now put them in a new chart. This is a higher level. We're doing a little higher level stuff here. Some of you thought you just had to memorize that chart. No. Now, if you're having a lot of trouble, here's what you did. You thought you just had to memorize the chart like middle school. Is that right? First of all, if I look at you like this rock, if I look at that rock and I can see you're made of more than one material, you have to be what? You have to be a mixture. And you're a heterogeneous mixture, aren't you? Okay? Now what? I had one year where I had one of these two charts on the test, and instead of putting homogeneous on the left and heterogeneous on the right, all I did was change it. And somebody thought, well, you changed the chart. Well, okay. I just put heterogeneous, see? And they thought all you had to do is just memorize it like a photocopy or something like that. That's not what I'm doing here. You're not learning anything by doing that. All right, how you doing? How many people, you're at a little bit of a roadblock? Okay, be honest.
I'm just like confused what we're supposed to be doing to it.
Okay, you know all the words are on this chart? You know all those words?
Oh.
Put all those words on this chart. You guys know what a flow chart is? Like this flow chart, like all matter. Matter is either a mixture or a pure substance. If you're a mixture, you're homogeneous or heterogeneous. If you're a pure substance, you're an element or compound. And now do it this way. What if the first question is, are you homogeneous when I look at you? Or are you heterogeneous when I look at you? Now how you put all those words in there? Are you going to branch this into two branches here? Are you going to branch this into two branches? Hey, thank you for saying that. So I'm not sure what I was supposed to do. That's a great question you had. How far are you getting? How far are you getting? Okay, that's fine. Look at everybody else. Do they look like they're confused too? Look at them. Look at them. They're confused too. What are you doing? Elizabeth, how you doing?
I'm confused.
Okay. Tiffany, Danielle, you don't look confused. Are you confused, Danielle?
Yeah.
Okay. Who's not confused? Two people? Okay. All right. Here's something you hadn't thought about, okay? what if I now ask the question about your composition? Who has constant composition, but when you look at it, it's homogeneous? Who has constant composition? Well, it goes here. This is an easy one. Sometimes a book just uses the word substance, but sometimes it says what? Same thing. Everybody got that? Well, then what goes here? When I look at you, you look like one material, but you're telling me that there's more than one way to make that? But I'm looking at it, it looks like one thing. What goes here? What is it? Uh-oh. Somebody said it. Somebody said it. It was way back there. What'd you say? No, what'd you say? Yes. And what is a solution? A solution is a homogeneous mixture. But see that? So I can't put two branches here because this mixture is a special mixture. It's homogeneous. It's a solution, isn't it? And it completely dissolves. One item completely dissolves in another. And so, yes, I could connect these two now, and I could say they're both mixtures. And underneath here, I could have alloys and stuff like that, all kinds of mixtures, okay? But now, I need to branch this off, don't I? There's two ways of being a pure substance. What are they? Right? And how do we know the difference? Elements are only made of one kind of atom, and they're found on the periodic table. Compounds are made of two or more different kind of atoms, chemically bound together, and they have a formula. Okay, now, do you think that I'm trying to confuse you by showing you this chart and then showing you this chart? Am I trying to confuse you or say, what if you really didn't know the difference between these words? Did you know that all pure substances are what? All pure substances are homogeneous, aren't they? But did you know that one of the mixtures is also homogeneous? One kind of mixture is also homogeneous. That's called a solution. All right, what do you think? All right, so what we'll do is let's go over the next thing, and I have some some demonstrations I may or may not get to. Maybe I'll get to them. Let's see, I might be able to get to them. Okay, so what I'm going to do now is, in your book, I'm going to go to some of the diagrams he had to draw. And let's take a look at some of them. You didn't have to draw that. And here is a table you had to draw. And we did a table like that, didn't we? Solid, liquid, and gas, remember that? And it has solid, liquid, and gas definitions. It has that there, and we had that little chart we had. And then he had this thing called physical properties and chemical properties. Remember that? I've been kind of doing that every chapter a little bit. Even when we do the candle lab, we talked about that. Physical properties says it has to do with not the chemistry of you, but the physics of you. For example, how much mass do you have? What color are you? Those are physical properties. But what's an example of a chemical property? Do you burn? Can I burn you? Will you react with acid? What if I say you don't react with acid? That's still a chemical property. Let's go on to the next one. You didn't have a diagram there. What about physical change and chemical change? Well, if you don't change your chemical nature, when ice melts, when gold is melted, is it changed? Is there something different about it? If ice melts, what is it made of? What was it made of before it melted? What is it made of after it melts? And you say, well, they're both H2O. So no, there was no chemical change. So what are all physical changes? What are all phase changes? Sorry, gave it away, didn't I? What are all phase changes? They have to be physical changes because there's no chemical that changes at all. So what I want to show you in some of my demonstrations is that a huge amount of time and money is spent in chemistry trying to separate things. There are many, many things in this country and many, many things in your body. They're actually made of mixtures. And the thing is, I need to separate them and then identify them. If you go to the doctor and you say, somehow I think you might have this disease that makes your copper, the amount of copper in your body too high, how do they know that? They had to take some of your blood, send it to a laboratory, and somehow separate that part from the blood and be able to analyze how much copper is in there. Now, how do we separate? Okay, we can separate by physical means or chemical means. Get that? Okay, now I need your attention on this next part. I don't know why every year some people miss a lot of these questions about whether it's a chemical change or a physical change. Think about this. If I take a piece of paper, oh, that's why I didn't get you. Okay. If I take a piece of paper and I think about the properties that it has, what kind of properties do you have? And here, let me have your hand, please. See that? See the properties? Look at your hand. See anything? One of the properties says, I won't leave a mark on your skin. Is that right? Another property is, I can bend it. Another property is what? I can tear it. Those are all physical properties. How much does it weigh? Physical property. But what if I do this? What do you think is happening here? Physical or chemical change? Burning is always a chemical change because you're actually taking the compound that made the paper and you're actually combining it with oxygen and making something brand new. Now again, I have to have evidence that there was a new material made. So this new material I have right here, does it have the same properties? Is that okay if I did that? Okay. All right. It doesn't even have the same properties, does it? It doesn't have the same color. It actually leaves a mark. If you want to wash your hands, you can. It's in there. Okay. Thanks for doing that. And this right here was a chemical change, wasn't it? Now again, why do people have trouble figuring that out? Do you think a new chemical was created here? There was. I don't remember anything like that before, do you? All right, so I have another one I'll show you. There's a picture at the bottom of page 58. All right, now, I have a poster that back here. I'll have to go to, oh, I don't see it right now. I have a big poster. Somebody did that for an extra credit year one year. This right here, you could actually do this at home if you wanted to. You need a big battery. Now, you can actually use a 9-volt battery. Does everybody know what a 9-volt battery is? Okay, 9-volt batteries, believe it or not, thank you for, a 9-volt battery is actually 6 batteries. If you took it apart, and again, please ask your parents before you do any of this stuff. If you took a 9-volt battery apart, you would see 6 little packets in that thing. Each of those packets has chemicals in it that undergo a chemical reaction, and when they undergo a chemical reaction, they will give off electricity. Now they have this thing called volts. Volts is, it has to do with what tendency do electrons have to push themselves around the circuit. Okay, it'd be like water. If you had water on a little bit of a ramp, the tendency to go downhill would be a little bit. That'd be like low voltage. What if I put the ramp like this? What's the tendency of the water want to go downhill now? And that's called voltage, okay? So voltage doesn't go anywhere. You set up a voltage. Well, so let me talk about this. Each one of those little packets has the potential to give you 1.5 volts. But if you hook them up, plus, minus, plus, minus. If you hook them up in a series, then you get to add those up, and you get 6 times 1.5, and you get what? What's 6 times 1.5? 9. That's why it's called a 9-volt battery. In my car, I have a 12-volt battery. It has 6 cells in it. 6 cells. The chemicals I use can produce a voltage of 2 volts. But they're connected, plus minus, plus minus, plus minus, plus minus. What is 2 times 6? 12. And that's how we get a 12-volt battery, like that. So anyway, now some batteries, a 9-volt can give you a lot of push, but they might not last very long. My car battery will give 12 volts, but it may last a whole lot longer than the 9-volt. So what I'm going to do is, let's take a look at that picture again. If you ever try this at home, the reason it won't work is because they don't tell you about this. If you hook electricity up to water, you should see, where you put the 2 electrodes, you should see bubbles appearing at both of the electrodes. And if I get a 9-volt tomorrow, I'll bring one on Wednesday. If I bring one, I'll actually do this in class. And if you put a 9-volt battery in water, you should see bubbles occurring out of both of those terminals. Now, it just so happens that, what kind of a change do you think that is, though? So, well, I don't know. Maybe those bubbles are simply water that got hot and turned into steam, but they aren't. And look at the diagram again. There's something you probably didn't catch on this. You notice that when you split water, and this is called electrolysis of water, do you notice that the column where it says hydrogen, what's the volume of hydrogen gas versus the volume of oxygen gas? Are they the same? There's twice as much hydrogen gas as there is oxygen gas, and that's an idea that water is made of what? H2O1. All right? And so if you do this thing, and why do they call it electrolysis? I love the name, but when you were in biology class, you probably learned the word lysis. Did you learn lysis? Did you have glycolysis? Okay, did you have, okay, lysis, when I used to teach biology, I used to teach that word, taught a certain number of Latin words. Lysis means to dissolve or destroy. And you can see there's a company even that said, what if you have a company and people want to buy our products because when they spread all over the counter, they think that they destroy all the bacteria. What would be a good name for that product? Well, it's a solution that lyses things. Lysol. See, Lysol is a solution that lyses things. And lysis means to completely destroy. Well, what happens here is electrolysis said, let's use electricity to do what? To destroy what? Water. And so it splits water into 2. And that's a chemical change, isn't it? All right. Now again, I'm running out a little short on time. Let me see if I might have enough time to do this. Let's go to the next diagram. Thank you for having your book. Let's go to page 64. On page 64, I'm not going to set that whole thing up because, it'd be neat to watch, but I'm not going to do that. This right here, somebody developed this. This is called a condensation apparatus. That's a fancy name. And you can see it on page 64. And so what we're going to do is, what if we have some salt water and I said, hey, you know what? I really don't want the water. I just want the salt. Okay, well, how are you going to separate them? Well, we could pour the salt water out on the table and wait a long time, and then the water will evaporate, and that would leave the salt, wouldn't it? There's one thing you need to know about mixtures. Mixtures can always be separated by ordinary physical means. Letting something evaporate is not a big major thing, is it? What about electrolysis? That's major. So every mixture can be separated by physical means. Hey, look at that salad. I don't think I'll take all the tomatoes out. I just separate everything in that salad by simply picking them out. Mixtures can always be separated by physical means. So, I have salt water, which is a mixture. I should be able to separate them, so what I'm going to do is heat the water. heat the salt water, and the salt will not, I will not get hot enough to change the salt into a gas. But I will get hot to water to change into steam, is that correct? Okay, now what happens to steam? Steam, because it's less dense, it goes up. And what happens then? Where does it go? I got my steam, and it's coming up, and what's happening? Where's it gonna go now? What's this? So I make the steam go in here, right? What's this all about? This is actually a tube within a tube. Okay, and what you do is, I would take some rubber tubing and hook this up to the sink and let cold water come in here. It will not go in here, it'll go in the outside water jacket. You might call it a water jacket, okay? And then this would go down the sink, down the drain. Cold water, down the drain. Cold water, down the drain. All I want is to surround this tube with coldness. You get it? I don't want the water to mix. And so the steam comes in, and what happens to steam if you take away its heat? It will condense. And drip, drip, drip. What'll happen here? Whoops. Hello. Okay, goodbye.
Teachers and students, please pardon the interruption. If you are in the choir and planning to go to Wellspring tomorrow, please stop by Mrs. Twiggs' office during break today to pick up a t-shirt. Thank you.
All right. It's playing with me. Okay. Wait a minute. All right, sorry, 110. All right, so what I'm saying is, what will come out here is just the water. And what will be left, look at your next drawing, what's left in the flask? Just the salt. Now, was I able to separate the salt from the water by simply boiling the water? That's all that's physical. It's a physical change like that. Now, if you ever watch movies or Andy Griffith every once in a while, you'll find out that the South was, matter of fact, NASCAR got its start by people who made a lot of alcohol illegally. There was nothing wrong with them making alcohol, but the problem was the U.S. government made money by the sale of alcohol. And a lot of people said, that's not right. I should be able to sell my alcohol, and not, I don't want to give the government any alcohol tax. They said they made it and they sold it. The government said, no, we want some of that money. And so they said, we don't want to give you money, so they would hide out and make their own alcohol. And sometimes the police would find out where you were and they would chase you. But if you had a car that was faster than any other car around here, they wouldn't catch you. And then you could have your moonshining operation. And NASCAR actually got started from that same thing. Now give me a couple minutes. 10 after, right? Can we go to 10 after? Oh, really? Okay, I'm sorry. Well, we'll end the conversation. We don't know what moonshining is. Anyway, it has to do with condensation. Hey, can you remind me to do moonshining first thing tomorrow?